Thank you, and thank you for having me here today. This work I'm going to present is an ongoing work that I'm doing in collaboration with Jonas Nikander and Casimir Delavergne. Here is the outline for this presentation, and it's organized around two main points. So we get first these Argo observations that we are going to use to tune a model. And this model was originally developed by Delavergne and colleagues. And what it is really is more like a simplified framework in which we aim to bring together different pieces of theory to model the propagation and dissipation of the internal tides in the ocean. But first, some background, and yes, you heard a lot about this previously already. So internal tides get generated by the interaction of tidal currents with rock bottom topography there. So the beams or the waves that are generated there can be decomposed into a set of vertical modes. And while the high modes are thought to dissipate locally, we also get low modes that have been observed to propagate for very long distances in the ocean. Now, as they propagate in the ocean, they are subject to a variety of dissipation processes. A few of them are represented there, and that will create mixing in the ocean entirely. Now, this mixing has been shown to have a large influence on the ocean state and therefore on the global climate system. Yet, few global climate models incorporate an energy constraint parameterization of this mixing that comes from internal tides. So the aim of this work is to use Argo observations to tune our simplified model and to get better representations of this mixing. Right, so these Argo observations actually come from a work that has been published last year. And I will start by trying to explain why these Argo observations are interesting to us. First, what we have a look at here is a map of the amplitude of the M2 mode 1 surface amplitude from satellite altimetry. In particular, this comes from the model HRET that is made by Geoffroy there. So this kind of picture of the internal tide fields offer very good horizontal resolution, and you can see very characteristic features of these internal tides with beams of waves that emanate from generation points. We call them hotspots. For instance, here in Hawaii. But the issue with such data is that the decay with propagation distance of these beams is not only due to the dissipation that the tides undergo. And the reason for that is that while they propagate in the eddying ocean, the internal tides get to interact with time-varying flows, and that causes the phase of the wave to be shifted. And the point is that altimetry can only pick up the component of the wave field that remains phase-locked with the astronomical forcing. Therefore, it misses a fraction of this energy. So that's what I wrote there. At any given point, one could decompose the wave field into a stationary fraction that is phase-locked with the forcing, and an unstationary fraction that is subject to this phase modulation. And where Argo is interesting is that it picks up the total energy field. So that's the one that will actually dissipate in the end. Now, the actual data we use come from the part phase of the Argo flows. So that's a typical Argo cycle. And before the assembly profiling sequence, that's the main data that we know from Argo. The flows stay adrift for about 9 days at a fixed level of 1,000 meters, during which they for some flows, not all flows. Some flows will then record temperature and pressure with a 1 hour resolution. So that's this time series that we use here. So we have 9 days of hourly temperatures records, and we use this then to compute the vertical displacement of the isotopes. So that's a very straightforward computation. If you have the temperature anomaly, you just divide that by the temperature gradient, the vertical temperature gradient that you can get from the profile, and then convert the temperature anomaly along the trajectory into the heading of the isotherms that will cross the trajectory of Argo. So that's the base data, and after some processing, then we get a global map that is the one on the top panel there. And this global map here shows then the total variance of the semidiurnal internal tide from observations at 1,000 meter depth. And now the bottom panel is the error associated with that. Okay, so one quick point about that. Actually, we found that this variance, which is half of the amplitude squared, is actually much larger than what was generally thought. So by comparing it to the projection of this HREF model at depth, we found that the non-stationary part of the energy is actually about 6 times larger than the stationary one. So having access to this total variance is quite useful information. Now I will skip this. This was just about validation of high resolution simulation with these Argo observations. The bottom line is that we found quite a good agreement with the high resolution simulation being biased low, but we could explain that by the fact that this simulation didn't resolve well high modes. That might explain the global bias there. And this model resolution decreases as you go forward, so that's also explaining why you get a larger bias down south. Okay, so we will use these observations to tune our model. Now, how this model works. So that's a simple Lagrangian tracking of the internal tide energy flux. So what the model takes as inputs is these global maps of the conversion rate, the barotropic to baroclinic conversion. So that's derived analytically, computed analytically. And it also takes as input global maps of the climatology to then compute the refraction of this energy flux as you propagate it. Then we have this Lagrangian tracking part of the computation. And as the energy flux is propagated, we also compute what fraction of this flux is dissipated along the way for each grid point. So that's as output, we get global maps of the dissipation and also global map of the energy content that is related to a particular constituent and mode of the internal tide. So I've recently been updating this model by using the new anisotropic conversion rate that has been computed by Frederica recently. Now, as she explained, the computation cannot be applied to the shell slopes, so she masked this out. And instead, what I use in these places is the conversion rate from ICOM simulation. So that is only for the M2 mode 1 internal tide, and that's just here. I use it as a demonstration just to show how this works. Right, so we have this energy flux that is generated at some topography, and then it is propagated by the Lagrangian tracking algorithm. And along the way, we have simple representations for these processes. So we have wave-wave interactions, topographic scattering by abyssal tips, And we have also interactions with the large topographic source that can lead to folding them. So that's an example with 3 source points. So we have an energy flux that departs from these source points and that is propagated in the stratification. And you can see then the energy flux decay due to these dissipation processes that we present. So at each midpoint along the way, we estimate how much it dissipates. We also have reflection at some points, transmission as well. So that's globally what we get for particular source points. And then we iterate that for all source points to get to these final results. So this is the energy content related to the M2 mode 1 internal tide. And we want to compare that with Argo. Now that's a bit tricky because, as you recall, Argo was only recording the variance at a single level, right? So we have to go from this single level variance to a depth integrated energy, which is not that easy because we actually cannot decompose the Argo variance into modes. We don't have this information from the Argo data. Yet there is the point there that we can argue that most of what is recorded at 1,000 meter depth is actually because of mode 1. So the bulk of the contribution would be from mode 1. An argument for that is that simply mode 1 is the most energetic on a global average. And the second point is from this plot, see. So for a quite typical stratification profile, if we compute the vertical modes, you can see that at 1,000 meter depth, we are generally close to the maximum on the untimed nodes of mode 1. That also corresponds to being close to a node for mode 2. So that would tend to magnify the contribution to mode 1 and lower the contribution for mode 2 from what is recorded. Now this is true on a global average, but that could vary locally. And we actually have a workaround then to estimate the contribution from individual modes to this variance recorded by Argo. I won't go too much into the details, but globally, this coefficient gamma is accounting for what I just said. So being close or far away from your node and anti-node. And we also need then an estimate of the energy model partitioning. So actually that's a big deal because we don't have that, and that's what we are after. But we can get estimates of that, for instance, from a numerical simulation. So that's what I did there. I used ICOM to estimate this model partitioning of the energy. Okay, so using this, we can estimate the fraction of the variance recorded by Argo that is due to mode 1. And we can simply use this variance of mode 1 to scale the mode 1 profile that will allow us to recover the depth integrated energy, right? So that's what we do. Actually, this gives you the potential energy, but you can use the polarization relation to get the kinetic energy and then get the total energy in the end. Right. So that is the result. The top panel here is the depth integrated energy from Argo, and the bottom one is the result from the model that I coarsened to the same resolution as Argo for comparison purposes. From there, you can see the global integral of the energy. From Argo, it's 34 petajoules and 33 for the model, which indicates a good agreement in a global integral. But then to see the variability and the differences between the two, I plotted here the ratio of the model to the Argo, or proxy for this ratio. So wherever you get blue color, it means that Argo is large compared to the model, and red then that the model is large compared to Argo. we would expect to get mostly blue because Argo actually do not make the distinction between the different constituents close to M2. So we also get S2 and other minor semidiurnal constituents there that would account for a larger variance in our energy number. So globally, that is what we get, mostly blue. But we have this red color then in the south. And on this side, don't have an explanation at this time. Here are density plots of the Argo compared to model. So we have good agreement, though we have some dispersion. And this is the same plot, but getting rid of this southern part of the data. So we have an even better agreement if we discard this red stripe close to the ACC. Okay, so how can we improve this model? Obviously, we can use more information in the generation of conversion rates. So that would be to add more constituents and more modes, and also get actually an analytic formulation for the conversion at the shelf. That would be nice. And on the propagation side of things, we could also get better representations of some of the processes. One being the wave-wave interactions, for which we have a pretty simple representation at this time. So here is the decay length related to wave-wave interactions. And this is simply based on this formula there, with a characteristic time tau, which is taken to be 20 days inside the range of the PSI, where PSI can add, and 80 days out of it. So that's pretty basic. Maybe we can improve there. And another point of interest for us then would be to add some parameterization of the interaction of these low mode intervaltides with the mesoscale features that could, we think it could add quite good information there. And with that, I thank you for your attention. We look forward to your questions.
Questions?